welcome to Rajashekar classes on Applied Data Science with Python. This is lecture number 385. In this lecture, we will try to understand cases of support vector machines. Now, let's look at various cases for support vector machines. First thing about feature engineering and feature transformation. In the case of SVMs, feature transformation is replaced by kernel design. So, you need to be able to design good kernel or use a kernel that works very well. So, the primary problem in feature engineering or feature transformation, specifically in the case of support vector machines, is all about finding the right kernel from the given problem. If you don't have right kernel, of course you always has RBF kernel as your default option. But if you find appropriate kernel for the given problem, support vector machine tends to work very well. Second thing is about decision surface. Decision surface of support vector machine. For linear SVMs, the decision surface is of course hyperplane. I will repeat. Second thing is about decision surface. Decision surface of support vector machine. For linear SVMs, the decision surface is of course hyperplane, and it's very simple. So for kernel SVMs, in the original space, in the d-dimensional space, your point xi lie, your decision surface could be a non-linear surface, isn't it? What does it mean? Your point, in the case of kernel SVM, just say this one, what happens here? In the case of kernel SVM, your point xi is in d-dimensional space. It is a non-linear surface, but by using kernel trick, this point xi can be converted into xi dash, where you can separate those points by using linear surface. This is d dash dimensions, this is d dimensions, isn't it? I will repeat. Second thing is about decision surface. Decision surface of support vector machines. For linear support vector machines, the decision surface is, I can say, hyperplane, isn't it? And is very simple. So for kernel SVMs, this is about kernel SVMs. In the original space, in the original space means what? D-dimensional space. Your points xi in the d-dimensional space, I can say xi is lie. Your decision surface could be non-linear here. In the d-dimensional space, this decision surface could be non-linear surface, and it could be of any shape. But because of kernel trick, we want take points xi from d dimension to other dimension d dash x, where you can find xi dash, isn't it? Typically, your d dash is greater than d. How can I do it? Using the kernel trick. Using the kernel trick, you want to take the points which are in d-dimensional space into the points in d-dash dimensional space. In d-dash dimensional space, higher dimensional space, you have linear surface. In original dimensional space, it is non-linear surface. That's what is the core idea of kernel SVM. Third very important thing is imagine if you are given similarity function, isn't it? Similarity function or distance function. Given a similarity or distance function, it's very easy to convert into kernel with few modifications. You can easily convert similarity function into a kernel. What is the kernel? Kernel again operates on 2 points xi comma xj. That is k of xi comma xj. We used to write like this, isn't it? When you have kernel, using SVMs is very straightforward. The biggest challenge with support vector machines is about interpretability, isn't it? I will repeat. The biggest challenge with support vector missions is about interpretability, especially about kernel SVMs and feature importance. There is no way that we can easily get feature importance for various features directly from support vector missions. Of course, we always has forward feature selection method, which is time consuming to get the important features, especially for kernel SVMs. For linear SVMs, it is very straightforward because linear SVM is about hyperplane. It's very simple, but for kernel SVM, it is still very hard. Which one is very hard? Your interpretation and feature importance is hard. The next important thing is outliers. Outliers have very little impact on your model, because if you think about it, only support vector missions, only support vectors that matters for model, isn't it? If you have an outlier, its impact is minimal, very small. But note that if you are using RBF with a small sigma, then what happens? Because this behaves very similar to KNN with small k, isn't it? KNN with small k will be impacted by outlier. RBF SVM with small sigma can also impacted by outliers. But in general, the impact of the outliers on support vector missions is very little, because only support vectors are matter, isn't it? Support vectors are important. Another thing is bias and variance trade-off. As C increases, you are going to overfit, because C is multiplied by loss function, which means you have high variance. Similarly, as C reduces, you are going to underfit the model, which means you have high bias term, isn't it? And of course, we have standard methods of grid search, isn't it? Standard methods of grid search cross-validation or random search cross-validation to find the optimal C. In the case of RBF SVM, we have two hyperparameters. We have C, which is multiplied with the loss. Your sigma, which is there as a part of RBF. C is multiplied by loss function, and your sigma, which is part of RBF. What happens if you have large dimensions, large D? If your dimensionality is large, that is very good for support vector missions. Given a data set in D dimensions, I can take you to a dimensionality. It tries to take you to higher dimension D dash, such that D is less than D dash, isn't it? It always takes from D dimensions to D dash dimensions. Relation is your D dash is greater than D, isn't it? At the start itself, if you have high dimensional space, SVM works like charm. The only thing is, if you have a good kernel, or if you don't have good kernel, you can always use RBF, and it works like a charm. When the dimensionality is large for support vector missions, no problem, they work very well. Let's look at what are the best cases and what are the we will try to understand best case and worst case. What are the best case? Best case means the best case for support vector mission. What is the best case? Just see. Let me show this one. Best case is, yes, just a minute. What is the best case? Yes. Let me select this one. Yes. What is the best case? Right kernel, isn't it? Let's look at what are the best cases. What are the worst cases for support vector missions? The best case for support vector mission is you have right kernel, then it is super good for support vector missions. For a given problem, if you have right kernel, then SVMs works like a charm. works like a magic literally. The worst case is when n is large, when your training data size is large, training time is typically high, which is not applicable for internet based companies. Worst case is when your k is large, k is number of support vectors. If your train model and suppose 90% of points are support vectors, then you cannot have low latency. It takes more time to compute f of xq, which means you can't use for internet based applications. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.